how do we solve the Schrodinger equation? Minus I h bar partial t psi. It's got to be a better one. Is equal to, oh, that's the same quality, h bar squared over 2m partial x squared psi minus u psi. Alright, so this is the Schrodinger equation. But what do we do with it? Well, we talked about normalizing solutions to it, but how do we actually solve it? Well, we use separation of variables. We assume that the wave function is a product of a function of x and a function of time. So then, how does that help us? Well, we can plug this in, and as soon as we plug this in, we realize that we can actually factor out a function of x from here. Well, it's only one term, so that should be fairly obvious. And we can actually factor out a function of t from here. So then, what happens if I just divide both sides by the product of those factors? Well then, this side becomes solely a function of x, and this side becomes solely a function of t. But wait a moment. The function of x and the function of t, if they are equal to one another, have to both be equal to a constant. Why? Well, imagine we have a of x is equal to b of t. What happens when we take their partial derivative with respect to x? Well, this becomes a prime of x, this is not dependent on x, so it becomes 0. Meanwhile, what happens if we take partial t? Well, this becomes 0 because it's not dependent on t, this becomes b prime of t, which implies that both a of x and b of t are constant because their derivatives in their respective variables are 0. We'll talk more about what this constant actually is next time. So, that gives us two equations. The first one is minus I h bar g prime of t over g of t is equal to c. Now, it's fairly easy to see that this can actually be transformed into a linear equation. And this just gives g of t times c divided by minus I h bar, and 1 over minus I is just equal to I, is equal to g prime of t. Hence, oh wait, hold up a second. I think I made a sign error. This is supposed to be plus. Wait. Let's keep it for now. No, I think it's supposed to be a plus. Okay. So, that means this is minus. Ow, my marker's dying. So, what does this tell us? Well, since g prime of t is clearly proportional to g of t, we now write that g of t is equal to e to the rt, since e to the rt is the only function that, when you take the derivative of it, gives you something proportional to the original function, aside from sinusoidal functions, but those are represented in this. And when you plug this in, that means that g of t is equal to e to the minus c over h I t. Doesn't matter. So that's g of t, which is fairly easy to solve. But then we're stuck with, I'm not using this marker, this side.
You can use the red one if you want.
the time-independent Schrodinger equation. So, how do we solve it? Well, your first step might be to enthusiastically multiply both sides by f of x. Then bring this to the other side. Factorize it. And happily proclaim that this is just a linear differential equation and that you can solve it as well. But there's a caveat. Because u is the potential function, which is always inherently dependent on x. And surprise, you can't solve it anymore because this is not a constant. You can't solve it without knowing what u of x is. So let's look through a few examples of what u of x is today and next time. So example 1, the infinite square web. So we're going to say that we have a potential function that looks something like this. Specifically, and I guess I can shade it in. So specifically, this is a function u of x that is equal to 0 if x is between 0 and a, and infinity otherwise. Now you might say, well, this isn't realistic, but it's an ideal scenario, and B, you can model it using several functions, most notable of which, for example, you can write as something like this. This basically models what we want pretty well as n approaches infinity. So now, how do we solve this equation with this potential? And first of all, what does this actually look like? Well, you can probably imagine that there's an infinite force at both sides preventing you from going further because, the function goes up from 0 to infinity in pretty much a second. And it goes from negative infinity to 0 instantly as well. So the derivative of u with respect to x at those points is going to have to be infinity or negative infinity. Doesn't really matter. And so the force at those points, remember force is minus d dx, but it doesn't really matter, is also going to be infinite, which means that the force here is going to be infinite in the positive direction, forcing it this way, and the force here is going to be infinite in the negative direction, forcing it this way. And in between, the force on the object is going to be 0, allowing it to just linearly bounce between the two ends. And you might say, well, what's preventing it from just going at infinite velocity? Well, remember that the force of infinite magnitude only occurs at this one boundary point instead of over an interval, which means that it's being applied for practically an infinitesimal time, which leads to a finite impulse. All right, so that's that. Now we know how the particle is going to act. How does the wave function look? Well, given the description I just said, you can probably guess that by Born's statistical interpretation, the modulus squared of the wave function outside the interval where the particle can bounce around is going to be equal to 0. because it's being stopped by these two walls of infinite force. There's a 0% chance that it's anywhere outside those walls of infinite force. And even if they were, they would be forced by an infinite amount of force. Well, no, actually, can't exactly define the force outside these two walls. So no, there's a 0% chance that it's anywhere outside these walls, because it's being forced to bounce between them with infinite penalty if it ever tries to go outside. Alright. So, we know that the probability of it being outside the wall is 0. So what about it being inside the wall? Well, inside the wall, u of x is equal to 0. So we can essentially rewrite this as minus c f of x. And suddenly, this actually is a linear differential equation that you can solve the naive way. So you can let f prime prime of x be equal to c times 2m over h bar squared f of x, which implies that f of x is going to be e to the rx, and r is going to be the square root of 2cm over h bar squared. Wait, hold up. Yeah, this is what makes me think I made a sign error. Oh, yeah. Okay. So I think it's better to just go with the old a cosine plus b sine form. So we write a cosine of but still that precludes something. Yeah, it precludes the imaginary part. Whatever. So we write it in this form. Yeah, but it also precludes like anything with the factor e to the rt. So this should be perfect. So let's see. If u of x is equal to 0, yeah, that gives us this form, which should work. So if f of x is equal to r, then f prime prime of x is, r e to the rt, f prime prime of x is r squared e to the rt, which means you get h bar squared over 2m. Yeah, there's a sign. Yup. Crap. This is minus, this is plus. Yeah, these two have the same sign. But still, how does that change things? Because, Oh, or this has a different outcome depending on whether c is positive or negative. Yeah, that does the trick. So, let's see here. But how? Oh yeah, c can definitely be negative, right? Because here, what did we assume about c? So now we're going to set f of x is equal to e to the rt, hence f double prime of x is equal to rx, r squared e to the rx, which gives us h bar squared over 2m, r squared minus c is equal to 0. So r is the square root of c, 2cm over h bar squared, or the square root of 2cm over h bar, which means that f of x is e to the square root of 2cm over h bar x. And if this is sinusoidal or just an exponential function, depends on whether c is positive or negative. Which means the final wave function is f of x g of t is equal to e to the, well, what was the solution to this original equation. We take the same sort of ansatz, I8 g prime of t is equal to cg of t, and so g prime of t is equal to, minus c over h bar I gt, and so we have e to the c over h bar I t, which means that here we have the wave function is equal to e to the c plus square root of 2cm over h bar I. No, I can't combine them like that. Okay, I over h bar times ct plus the square root of 2cmx. There we go, that works. So this is our wave function over this interval. And outside this interval, it's going to be 0. But of course, there are going to have to be a few boundary conditions, because the wave function has to be continuous, even though it doesn't necessarily have to be differentiable. Which means that at 0, this has to be 0. At a, this also has to be 0. So what happens at those points? Well, at x equals 0, this becomes e to the I over h bar ct. When is that equal to 0? Well, let's expand this out. This gives us cosine c over h bar t plus I sine c over h bar t. So is it never 0? Yeah, because it's an exponential function. So why would it be 0? Unless c was equal to 0. But even in that scenario, e would just be equal to 1. So, no, but the minimum this can go to is a 1. Well, no, technically not the minimum, but it can't ever touch 0. Hold on. Unless there's a constant factor that I'm missing. So, without accounting for constant factors, this is about the best we can do for an infinite square well. But what happens with a finite square well? Well, a finite square well is going to be very similar, but instead of being forced away with finite force, infinite force, sorry, you are now forced away from the boundaries. Well, it's still an infinite amount of force, actually. So, what happens if we have something like this? So, we're going to call this, I don't know, n. U0. Okay, that works. So then, you can probably expect that inside this shell, we're going to get 0 from 0 to x to a, but outside this shell, what are we going to get? Well, you're probably already thinking, well, the probability has to be finite over the whole real line, which means that, unless we want it to be non-normalizable, which means that the wave should decay, or otherwise the integral is not going to converge. So, how can we make sure that this wave is going to decay? Well, that always happens if you have e to the minus something multiplied by the sinusoidal functions that you want to decay. So, our solution outside the walls is going to take something similar to this form. So, what happens if we actually do that? Well, here, this is now going to be plus u0 f of x, which means that the c here is actually going to look more like plus u naught minus c, which means this is getting shoved in as 2c minus u naught m divided by h bar. And if u naught is bigger than c, or vice versa, then we're going to decay. Wait a second. So then, if we replace this with 2 times c minus u naught m, then this is going to start decaying because of the extra u naught factor. So instead of looking like this, like our regular wave, the new function is going to look a little something like this. So that its integral will decay as you approach infinity from both sides.